today we are going to talk about the power rule, the product rule, and the quotient rule. These three rules are going to make our lives so much easier. And there's a couple other ones in there that I've thrown in, but these are the main three. These rules are going to make it so that we don't have to do the limit of the difference quotient as h goes to 0 anymore. It'll allow us to jump straight to the chase, which is awesome. Because I'll be honest with you, doing this limit of the difference quotient stuff, especially when it's really like a really big long function, it's a pain in the butt. Ain't nobody want to do that. But here, with the power rule, basically what we can do is we can say, all right, if we've got a polynomial of any kind, we can take the exponent, bring it down and multiply it to the coefficient, change the exponent to one less than it was, and that's the derivative. Or if you have a constant, then the constant just derivatives away, right? Because remember, the derivative is the slope, right? If the numbers are the same all the way through, it's a horizontal line, so the slope is 0. Remember we talked about horizontal line means the slope is 0? And so, like, the power rule, and the book that we have refers to this as the constant multiple rule. I just wanted to make sure that was in our brains here. Okay, so let me push forward with a bunch of examples. We're going to see a bunch of examples right now. All things that you can do with the power rule. Let's look at this first one. We got y equals negative 6x to the fifth plus 1. So if I want to take the derivative of this, if I want to find y prime, I'm going to take the derivative of each of these pieces separately. So look, I'm going to take this 5, boost it down here, and turn the x into a 4. And then I'm going to do 5 times this negative 6. That's this part. Derivative finished. Now let's do this part. This is just a number. So the derivative of just a number by itself like this is 0. And so now that is my derivative for this one. And the great thing is, like, you could, with something like this, you could just keep on taking the derivative. What if I wanted to take the second derivative? Y double prime? Well, then I'd take the 4, I'd boost it down, and then I'd get 4 times negative 30, negative 120, and I bring the exponent down 1 to 3. So I can even, I'll put that there too. I won't be able to do that with all of these, but. And you can keep on going. The third one, the third derivative, you again times 3, turn that x into a 2. The fourth derivative, negative 720x. The fifth derivative, you can just keep on going. Now here, the exponent was 1. I bring it down, it doesn't change. When I take the derivative of just an x term, the x goes away. And then the sixth derivative, I could even keep going again, right? The derivative of a number is just 0. And if I were to keep on going, this would still be 0. Hold on, wait, I want to find the meme, because it's funny. Yeah, because you could keep going. You could take the 15th derivative, but it's not going to change from there. Just not going to change at all. But so that's sort of the point here, is that you can keep going with these. I'm not saying that you're going to be told to, but like I can find the first derivative, and then just proceed straight to the second, to the third, to the fourth, to the fifth, to the sixth. So let's look at this next one now. Same idea, right? 7t to the fourth minus 4t to the seventh. So we're taking the derivative of t. I'm going to use a different notation this time. The derivative of s in terms of t. So I'm going to bring down the exponent. 4 times 7 is 28. Bring this down by 1. It was a 4, now it's a 3. Minus 4 times 7 is 28. Bring this down. It was a 7, now it's a 6. And you can keep on going. I want to take the second derivative. It would be like this. D squared s over dt squared. That's the notation for the second derivative. You might see that sometimes. And again, just bring down the exponent, multiply it in, and get what you get. 28 times 3. What was that, like 84? Sure, we'll go with that, 84. And then bring down the 3 to a 2. 28 times 6. Right, and so you're just taking the derivative the same way each time. Bring down the exponent, make the exponent 1 less. Bring down the exponent, make the exponent 1 less. Bring down the exponent, make the exponent 1 less. That's all we're talking about with these. Don't overthink it. These are really, really easy once you do them a couple times. All right. Now, let's look at this third one here. This third one here feels a little weird because like the exponents are here. Here, let's put a 1 here. But then it's like that's -2. What is that even? Well, you can have negative exponents, right? Just like you can have fraction exponents. You can have any kind of exponents you want. As long as it's an exponent, it'll work. So I want to take y equals 5x squared minus 15x to the first minus 9x to the -2. And I'm going to do the exact same thing I did before. I want y prime. This is a 2 in the exponent. Bring it down. 5 times 2 is 10. I dropped the 2 down to a 1. Hey, there we go. Minus 15. I'm going to take the 1, bring it down here. That's still 15. Bring that down. The x goes away, right? X to the 0, x goes away. There's 0 x's now. And then this one, again, I'm gonna bring got a 9, and then you've got bring down the -2. So -9 and -2 actually makes positive 18. And then I'm going to take the exponent, I'm going to bring it down 1. It was a -2. Now it's going to be a -3. I'm just going down 1. The process is always going to be the same here. And you can keep on going and doing the exact same thing. I'll show you one more. Again, this is 10x. So I take the derivative and I'm just left with 10. The minus 15, well, that goes away. Take the derivative of a constant, it goes away. And then the 18, we're going to bring down the -3. Anyway, so like I said here, take the 10x, take the derivative, you just get 10 because the x goes away when it's just to the first. The -15, that's a number. So when you take the derivative of just a number, it goes away, it becomes 0. And then lastly, we've got this 18x to the -3. Bring the -3 down, and that's -54. And then x to the, what's the next one? Well, -3, we go down and we get -4. All of these, it's the same thing. Same process each time. And if you can sort of generalize this process in your brain, it's going to make your life super duper mega extra easy. Okay? Okay, so let's do the next one now. This one, again, it looks weird, but it's not that weird. Because look, I'm going to rewrite it. Before we even start, I'm going to rewrite it. We've got 1 over 3 times s squared minus 8 over 5 times s to the fourth. So here's the deal. First of all, let's get rid of the numbers. Let's rewrite that as a fraction. Now let's take this s squared that's in the denominator and rewrite it as an exponent normally. So this is really 1/3 times s the quantity to the negative 2, right? Same thing here. I'm going to take this 8 over 5. I'm just going to rewrite the 8 over 5. I'm not even going to bother trying to think about it. And then this is going to be s to the negative fourth. And then it's no longer in the denominator. It's just hanging out here on the side, right? 8 to the fifth times s to the negative fourth. Well, then let's do this. Let's take the derivative. What is r prime going to be? Once again, I'm going to bring down the negative 2. So this is now negative 2/3. And then s, we're going to have the negative 2 go down to negative 3. Then we're going to do the same thing. We've got the negative 4 is coming down, so negative 8/5 times negative 4 is positive 32 over 5, right? 8 times 4 is 32. The two negatives cancel out, become a positive. This negative 4 drops down. It was a negative 4. Now we're going down 1 to a negative 5. And it's the same idea. It's the same idea each time. All right? And this is our r prime. Same thing, same idea with this this one down here. These radicals, you can do something very similar with them. Okay? So what are we going to do? Why did I click on that? What are we going to do? Let's look. So like rewrite this again. So first thing to rewrite this, let's do this. Let's split the denominator up like this. Let's start by doing that. Make our lives easier. Now, we know how to deal with this because we did it in the last problem. 7x over x, isn't that just 7? And then how do I deal with that radical? Well, so the formula that we use is this, right? Using a fraction exponent, the whatever the index is here in the radical becomes the denominator. Whatever the exponent is on the thing on the inside becomes the numerator of the exponent. So this, let's rewrite, because that's a 1, that's a 2, right? So let's rewrite this. So this is 3x to the negative 1. These cancel out, so this is plus 7. And then this one, this is really x to the 1/2, right? Our exponent rules say that we subtract the top minus the bottom, right? So this is minus 4 times x to the negative 1/2, right? And now we can just do the exact same thing. Can you imagine trying to do this like we did it on Tuesday with the limit of the difference quotient? Never, right? So look, take the derivative. Bring down the negative 1. Bring down the negative 1 to a negative 2. this goes away, right? The derivative of a number is just 0, so it goes away. Now we bring down the negative 1/2. -4 and negative 1/2 make positive 2. And then we're going to go down 1. Down 1 from negative 1/2 is negative 3/2. And there it is. All right, we got 2 more on here. Let's do them. But this one's really cool because they're trying to make you think real hard. We know how to do this one, but we're saying, okay, well, how do I deal with e to the 4th? E is a number, right? E is 2.718281828 something 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 something. E is Euler's constant. And so this right here, this is like, it's almost like it's the number 5, whatever. It doesn't matter what it is. It's just a number. So when I take the derivative, it's just a number. It just goes away. So when I find S prime, let's do this one, bring down the 5/3. 6 times 5, 30 divided by 3 is 10. And then 5/3, we're going to subtract 3/3, right? 1 whole. And be left with 2/3. And then this thing is a number. It's like E is a little bit less than 3, so 3, 9, 81 times 8, whatever that is, 640 something. So this is like just the number 640 sitting right here. We take the derivative of that, it just goes away. We don't care. So that's it. That's the derivative there. This thing. So again, all you're doing is you're taking the exponent, bringing it down to multiply with whatever's out front, and then taking the exponent and moving it down 1. That's all it is. That's all it is. So let's do our last one right here. So we're going to say, all right, well, let's rewrite all these so that they work. Because this is x to the 6 over 7 power, right? Minus x to the e power. And again, don't let the fact that that's an e confuse you. E is just the number 2.718281828 and so on. So like I go through, here's what I'm going to do. I'm going to be like, let's bring down that 6 over 7. Subtract 1, so that leaves us with x to the negative 1 over 7. Minus, well, let's bring down the e. And then now we're going to take e and go down 1. If it was 5, I'd go to 4. If it was 10, I'd go to 9. If it was 3.5, I'd go to 2.5. This is 2.71828. So it's going to be like 1.71828. But you can just rewrite it as e minus 1. You don't have to do a lot of extra. Don't do extra when you don't have to. There's no reason, you know? So that's the power rule. We did a whole bunch of examples just now of the power rule. But like that's all it is. This is your replacement for using the limit of the difference quotient. Let's look at the next thing. The exponential rule. So on the other hand, so like before when we were looking at the e stuff here, e to the 4th is just another number. But now if you've got e to the x, you've got some special rules. This is an exponential function. So if we do e to the ax, all we do is bring that down. And then the derivative is just a times e to the ax. And So this does mean, like, if a was 1, then the derivative, like if it was just y equals e to the x, then the derivative would just be e to the x. I've got this little snazzy cartoon here. All right. So this is your thing. If you go through and you have e to an x, then you can use this right here. All right. Let's do some examples. So we're going to do it. We're going to say, all right, y equals 8 times e to the negative x plus e to the 3x. Well, let's take the derivative of that. What's y prime going to be? Well, let's bring down the negative 1 and then just rewrite the e to the x part. The second part, let's bring down the 3 and just rewrite the e to the 3x part. Don't overthink this one. Same thing here. Let's do this one. Notice that there's a lot of different mix of things happening for number 2, right? So let's look at each piece one at a time. Don't try and do it all at once. If you do it all at once, you're going to go insane. Do each part on its own. 8x to the 5th over 5. Well, let's bring down the 5. 8 times 5 is 40. Divided by 5 is 8. And then x to the, it was 5, but it's x to the 5th, so we're bringing it down, and now it's x to the 4th. Let's do this one, negative 5x. Well, when we have negative 5, when it's just a linear term with just an x term, we take the derivative and the x just goes away, right? And then here, now here's our exponential term, 7 times e to the x. Well, wait a minute, hold on. What's up here? It's just 1, right? So if we brought down a 1, that would still be 7. And then we rewrite our e to the x term. And then we're good. So here's our derivative. Here's our y prime. Here's another one. Same idea. We've got a polynomial term, and we've got an exponential term. So let's do them both, one at a time. Bring down the 6 over 5. And now we're going to subtract 5/5, right? 1. We're going to subtract 1 from that exponent and get 1/5. And we're going to do this thing here. We're going to bring down the negative 2. And remember, the e to the x part stays the same. So it was a negative 2x. It stays a negative 2x. And that's it for these. So that's what we call the exponent rule, or whatever, the exponential rule. If you've got e to the x, we'll talk more about other exponentials later, where it's not e to the power of something, it's like 2 to the power of something. We'll talk about that down the line. So now let's talk about the product rule. So like the product rule, basically, if you've got two different things being multiplied together that have an x in them, you can sort of break them apart. So it's left times right here, if that's your thing. Then your derivative is left times the derivative of right plus right times the derivative of left. Left d right plus right d left. Okay, so let's look at some. Here we've got two functions multiplied together. We got x to the 11 is one, e to the x is the other. So let's use our product rule. Now, I like to help myself and actually label everything. To me, it helps. You don't have to. No one's gonna force you to do that. But what I'm gonna tell you is if you're in a like, because I don't want to do all that in my head. Nobody wants to do all that in their head. Do it on paper. So f was x to the 11th, so f prime is 11x to the 10. G of x is e to the x, so g prime of x is e to the x. So now we can fill it out. Left d right plus right d left. So we got y prime equals left times the derivative of the right plus the right times the derivative of the left. And if you write that for your answer for the AP test, you're done. That's everything you needed to do. You don't need to do any more. Now you could clean it up. This first part not so much, but the second part. Just if you're one of those people like me, I like to have the number out front. But it doesn't matter. Either of these answers are correct. Why give more work for yourself by writing it out again, right? Okay, let's do some more. Again, it's more of this power rule stuff in here. So look at this one. Left d right plus right d left. Let's find our left. Well, our left one is 6 minus x squared. Take the derivative of 6, that's 0. Take the derivative of negative x squared, we get negative 2x. Now let's do our g. X cubed minus 2x plus 3. Now I'm going to take the derivative of that. What's the derivative of x cubed? It's 3x squared. What's the derivative of negative 2x? Just negative 2. What's the derivative of 3? 0. So we don't have to write it. Now, once again, left d right plus right d left. 6 minus x squared times 3x squared minus 2 plus right d left. X cubed minus 2x plus 3 times negative 2x. And again, I could simplify this. Maybe one day when like we have to say take the derivative again, maybe we want to simplify and get it easier to work with. That's fine, but why would I do more here? This is my answer. On the AP exam, you can literally just leave it like this in this hot mess, and they'll have to look at that and go, okay, is that right or no? So just be aware. You totally can just leave it. Leave it as a hot mess. Make those graders earn their money. Okay? But I'm telling you from experience, from someone who's tutored calculus now for a good decade. I used to tutor calculus when I was just getting started, make some money, and so I'd go through, and the kids who wrote this down were more likely to get the problem correct than the kids who didn't. Same thing with this one, right? My left, here's my left. Here's my right. So and eventually, I'm not saying this is going to always have to be what it is. Like you're saying, "Oh my god, this is so much work." Okay, fine. But like eventually you're going to get so good at this where you could potentially do some of the easier ones in your head, or at least sort of skip a bunch of steps because you understand it. I'm going to rewrite this in terms of making them all polynomial properly. I'm going to do this last one, 7 times x to the negative 1, right? That in the denominator. We don't want it in the denominator. So let's take the derivative here. Derivative of 5x is just 5. Derivative of 4 is 0, so I'm not going to bring anything down. Derivative of this guy right here, bring down the negative 1. It's now negative 7. And then this is going to go down from negative 1 to negative 2. There's my left d right and right d left. Left d right plus right d left. That's a 4. But yeah, it's not designed to be difficult. Don't let it be difficult. All right, here we go. So now, again, we're gonna have to do some rewriting before we can use our product rule like we want to. 6e to the w times 1/7 w negative 1, right? W to the negative first. Now I can do it. Here's my left, here's my right. So I go right, and then we try to take the derivative of e, but it doesn't change. And then here's your g. Your g prime. So we bring down the negative 1. So now that's a negative 1/7. And we change this negative 1 to a negative 2. Once again, left d right plus right d left. And you can just multiply all that together. I'm just going to cut to the chase right here. Here's our r prime is negative 6/7 e to the w to the negative 2 plus 6 to the 7th e to the w to the negative 1. This last one, you have options, a lot of options. You can say to yourself, I don't want to have to deal with the fact that there's 3 of them. You could take one of these, a couple of these, and FOIL them together. You could do that. It would take a while, but you could. Or you could try and generalize it. Generalize our multiplication rule, right? We could say, all right, well, let's say there's an F, a G, and an H now. Well, if I follow the pattern, it should look like this, right? Basically, where one of them is the derivative in every group, right? Here's the F1, that's the derivative first. Here's the G1, that's the derivative. Here's the H1. And so now let's look at the F primes. So the derivative of x is 1. Derivative of negative 2 is 0. Well, there's F prime, right? What about G prime? Oh, it's also 1. What about H prime? Well, that's also 1. Hey, that makes life a lot easier because now I can, okay, well, F prime is 1, so I'm just going to do G and H together, right? Now G prime. Well, that was 1, so I'm just going to do F and H. And then here, H prime. Well, that was 1, so I'm just going to do F and G. And this would be your answer. And again, the knee-jerk reaction here is to try and distribute all this out and combine it. If you're on the AP exam and you leave your derivative just sitting like this, you will get full points. Just leave it like that. There's no reason not to. Okay? Product rule. Quotient rule. Okay, it's the same thing over and over again here. I just have a lot of different ways to write it. This is the way that I always learned it. Low d high minus high d low over low squared. Low d high minus high d low over low squared. Here's a really clean looking here if you've got a fraction here looking like this. Here's another representation. It's all the same thing. It's just different representations. I'm a big fan of low d high minus high d low over low squared. And I heard somebody call that the yodeling formula. Low d high, high d low, yeah. Low d high minus high d low over low squared. The yodeling formula. But let's do some of these. So, again, make your low, make your high. Well, what's the derivative here? It's just 3, right? What's the high? What's the derivative here? Should just be 8, right? So now, low d high minus high d low over low squared. Ta-da! It's done. The evil has been defeated. Low d high minus high d low over low squared. And again, you have the urge to like simplify your fractions and stuff, and that's all nice and kind of you, but why? Don't. The AP grader is going to give you the same points whether you leave it here or whether you do the rest of the work. Leave it there. Just leave it there. If that's what they want, what's the derivative of this function? That's the derivative. Just do that. All right? Low, high. So what's our d high? Just 7. What's our d low? 2x plus 9. Does everybody see why this is 2x plus 9 when we take the derivative? So now again, low d high minus high d low all over low squared. And as I said before, the AP exam is not going to penalize you for not simplifying. You leave it like this, you have gotten your answer. Don't try and do anything special. All right. Now with this one, with this third one, just be aware it's written funky, but it's the same thing. All right, I'm going to erase this real quick. Again, rewrite it so that it looks like it's supposed to. Right? Just rewrite it like it's supposed to look. Look, here's my low, here's my high. Now it's the exact same problem as this one basically, right? D high is -1. D low is 2t. Now you can do your low D high minus high D low over low squared. Just put the negative out there. Minus high D low over low squared. And then that's it. There is my prime. This last one, it's not different. Radical s is just s to the 1/2. So d high is just 1/2 s to the -1/2. D low is the same thing, 1/2 s to the -1/2. And then again, it's the same exact thing. Low d high minus high d low over low squared. Okay, so those are our rules. Now we have other problems I just want to show you because they're good problems to dissect and talk about, especially with the directions. The directions are super important for a lot of these, so I wanted to go over them. So let's look. Suppose u and v are functions of x that are differentiable at x equals 0, and that u of 0 equals 5, u prime of 0 equals 7, v of 0 equals 9, and v prime of 0 equals 4. I want to find the values at x equals. So here, look, this is the product rule, right? Left d right plus right d left. And then we know all of these, right? At 0, u is 5. V prime is 4. V is 9. U prime is 7. So this is just 20 plus 63, 83. Same thing with these, right? Low D high minus high D low over low squared. And so now we can just plug it in, just like we did before, right? We got, I'm going to cut to the chase a little bit. V times U should be 63, just like it was up here. U times V had better be 20. V at 0 is 9, so this is 81 on bottom. You can just leave it there. Like, remember what I said, you don't have to simplify. You can leave it there. The AP person won't like you, but they will give you full credit. You don't have to say that that's 43 over 81. You don't get extra points for simplifying. Same thing here. Now it's just that the U and the V are flipped, right? So this is right. So same thing up top, basically. It's just backwards from each other. We got 20 minus 63. What's U at 0 is 5, so over 25, right? And again, you don't have to do anything with that. You don't have to make it negative 43 over 25. You don't get extra points for simplifying, and you're on a limited time, so you might as well leave it here where it is. There's no trouble there. All right, now I wanted to talk about this one because like people are going to be confused. Well, but that's a minus sign, right? Remember, we can take the derivative of both of these separately, right? You take the derivative of both separately because it's a polynomial type thing, right? So instead of it being negative 2v, when we take the derivative of negative 2, it's going to be v squared, v prime, sorry, prime, minus 2u prime. And then we just plug in our numbers. V prime is first, so this is negative 8. U prime is 7, so this is negative 14. Negative 8 minus 14. You could put negative 22, but remember what I said. You don't even have to go that far. If you really wanted to, I wouldn't, but if you really wanted to, you could leave it as... You could leave it there. You don't have to do negative 22. Any of these three answers with the correct work shown with it will give you full points. Seriously, I do mean that. On the AP exam, they will give you full points for any of these three. Okay. So remember we were talking Tuesday and many other times about how we're going to get the exact same problem said in 1,000 different ways to do the exact same thing. Find an equation for the line perpendicular to the tangent of the curve. So perpendicular, this is a little bit of a twist. We'll talk about what that means in a second. Perpendicular to the tangent of the curve at the following point, 2, 6. So x, we know x is 6. You know, let me try that again. We know x is 2. We know y is 6. It's our x1 and our y1. And here's our curve. So what we need to do, we'll hold on to this perpendicular for just a second. But like here, all I need to do, tangent to the curve, I want to find the slope again, right? Well, let me find the slope. Let me take the derivative. This time I don't have to do the difference quotient with that god-awful thing. Just take the derivative. Right? Well, then I want it at x is 2. Well, let me find what that is. Four, 12 minus 4 is 8, right? So the slope at 2 is 8 on the curve, the tangent line. But we want perpendicular to that. Remember, perpendicular, and by the way, there's another phrase that you'll see sometimes. This is called the normal line. Tangent line is, so here's your curve. You got the tangent line, skips right off. The normal line is the one that goes through. Let me different color so that it stands out better. The normal line is at a right angle to that tangent line. So what we're trying to find the green one. What we've got is this one. So in order to find the slope of the new guy, it's opposite reciprocal. So the perpendicular slope is going to be opposite. It was positive, now it's negative. Reciprocal, it was 8 over 1, now it's 1 over 8. So the slope that we care about is -1/8. The point that it's happening is 2, 6. So now I can write my equation, y minus y1 equals the appropriate slope times x minus x1. Voila! That's this guy. Okay? That was part A. And again, I'm taking this slow. This doesn't take that long. I am doing this for demonstration purposes. When you get good at something like this, it will literally take you 15 seconds to go, okay, the slope is this, plug it in, yada yada yada. I brought this up mostly to say, hey, look, it's happening again. But the real reason why I care about this problem is part B. It's a really snazzy problem because part B is very interesting. They want to know what's the smallest slope on the curve. They want to know where is the slope the smallest. Now, I don't want to reinvent the wheel. Let me bring some of this back here. This is the function. This is the function that represents the slope for any x. And we want to know where this gets to be the smallest. There's a lot of different ways you can do this, and we're going to be able to do this in a different way a little bit later. But for right now, think back to Algebra 2. I don't know who you had for Algebra 2, but hopefully you talked about the vertex of a parabola. -b/2a. Well, now if we look here, here's our a, this is our c, b is 0. So we're going to be like, okay, well, 0/2 times 3, that's still 0. So my x value, where it's the smallest, is 0. And now I can go back to the original function and say, well, this happens at the point 0, 6. That's the second part. And then what is the smallest slope? Well, what if we plug 0 in? Well, this is where it is. So let's plug in x here. That's just 3 times 0 squared minus 4, which is just going to be -4. So what's the smallest slope going to be? -4. That's where the vertex is. That's where the slope is the smallest. And then part C, find the equations for the tangents to the curve at the points where the slope of the curve is 8. So here, again, we're going to use the slope. We're going to say, okay, well, that's got to be 8. Well, let's find out where it's 8. Let's do that. Where's 3x squared minus 4 equal to 8? Let's solve. X squared equals 4. So x is 2 and negative 2. Don't forget, we take the square root. We got to do the positive and the negative, right? These are our two x values. Now we want to find the equations for those tangent lines. So we found x. We need to find y, and we need to find m, right? So we've got for x equals 2, y equals 2 cubed minus 4 times 2 plus 6. So this is 8 minus 8 plus 6 is 6. So here y equals 6. And the slope, we go back to the slope function, the y prime. And x is 2. 2 squared times 3 is 12. So the slope is 8. And then so here's our x, here's our y, here's our m. Y minus y1 equals m times x minus x1. And I'm going to, this is for x equals 2. I'm going to leave x equals negative 2 for you to figure out on your own. Okay? All right. So let's, I've got a lot of these problems. Again, it's the same thing. It's just different applications of the same thing. So you can, so a lot of these are on your homework. If you come up to these and you want to go through any of them, we can. But I did want to talk about these last two most of all. So this is an alternative way of writing the difference quotient. F of x minus f of a over x minus a. And so if you have a function written this way, you can just read off what f of x is by looking right there. This is what f of x is. This is your f of x. Why is that important? Because here, that's part A right there. And then what's the number A? Where's A that we're going to? Well, isn't it 1? And then now we have f of x. What's f prime of x? Isn't it just this? And then it just wants us to say, well, 1 is what x is. So what's the slope? And then just 170 times 1 to a power. 1 to any power is 1. So the slope, which is what part B is 170. Okay? Now this one. So what you want to do, one thing that we need to talk about, making this function differentiable. There's a phrase that I want to tell you. Differentiability implies continuity. So if it is differentiable, it must be continuous. If it is differentiable, then it must be continuous. Differentiability implies continuity. So that is to say, if we know that it's differentiable, then this had better be continuous. That is to say, we're going to say, well, x is 0. That's the place, right? That's the only place where there could be a break. So if x is 0, then we need to figure out what makes this the same, right? And the other thing that we need to be able to do is say that the derivative must also be continuous. Because here we plug in 0, we don't get anything, right? We plug in 0, nothing happens. It's just 0 equals 0. So what we have to do is we have to go to the derivative now. So we look at g prime of x, and it's a, and the other one's 2x minus 11, right? And this is at x equals 0 that we care about. I mean, the domains are what they are up here, but we don't care about it anywhere else but 0. So now we can plug in 0, and we're actually going to get a equals negative 11. And that's what the value has to be in order to make it continuous. And that's what the value has to be to make it differentiable.